Emission Spectra Part 2. Niels Bohr was using a spectrometer to study atomic emission spectra. He was expecting to see a continuous spectrum of light emitted from the tubes, but instead observed lines. If only certain colors of light are being emitted from a gas tube, then only certain wavelengths are being emitted as well. If we assume the one we're looking at is 700 nanometers, we could use an equation to calculate its corresponding energy. This energy would be an energy change that's going on inside of the gas tube. A lot of times people think that the lines are energy levels themselves, when in reality the lines are actually energy changes that are going on, that electrons are undergoing. If you think about it, radiation leaving the atom means that something inside of the atom has to be less energetic. We're assuming that the energy coming out is coming from electrons losing energy. Those energies can be turned into wavelengths using the equation, and if the wavelengths are visible to our eye, we perceive them. This is in keeping with Max Planck's idea of the quantum. Remember, he said that all energy changes in the universe must be a whole number multiple of h nu. If it's not a whole number multiple of h nu, it's not allowed. The black areas in the emission spectrum are changes that are not allowed inside of the atom. Scientists were still concerned with explaining why hot metals glow. Typically, when people talk about Bohr's work and addressing this question and others, they use two main models. Both of these things are models. It's important to understand that neither one is exactly what you would see if you were able to look inside of an atom. They do, however, have common features. Both have energy levels which are labeled with n's. N equals 1 is energy level number 1. Both also have an energy axis that shows that as you move away from the nucleus, you become more energetic. That means that an electron in energy level 3 would have more energy than an electron in energy level 1. Bohr explained the hot metal glowing by saying that every electron has a ground state. This is a minimum amount of energy that it needs to maintain to keep it from spiraling into the nucleus. Electrons are attracted to the positive nucleus, but if they maintain their ground state energy, they can exist outside of the nucleus. Bohr theorized that when energy enters an atom and is absorbed by an electron, that electron moves from its ground state to what's referred to as an excited state. Higher energy states are not stable, and they don't last for long. And almost immediately, the electron returns back to its ground state, emitting the very same amount of energy that it had to gain to get to the excited state. These red arrows sometimes lead people to believe that the electron is traveling between energy levels. Remember, allowed place 1 and allowed place 2 are where the electrons can be, and not in between. Those places and corresponding energies are not allowed. When that energy is emitted, it has a corresponding wavelength. Depending on what the wavelength is, we may perceive it as color. Keep in mind that the wavelength could exist and might correspond with another type of radiation that we can't see, something like UV or IR, for instance. Also keep in mind that if you attempt to give an electron an energy that will place it at an unallowed state, that energy is not absorbed and it goes straight through the atom and the electron is unimpacted. Also keep in mind that ground level need not mean n equals 1. Some electrons have a ground level state that's higher than n equals 1. And when they undergo changes, they have energies that come out, and those energies may correspond with wavelengths that we can see with our eyes.